Have you ever planned your whole weekend around a sunny forecast only to have it completely washed out by rain? Yeah, we've all been there. Well, get ready because the entire world of weather forecasting is in the middle of a massive shakeup, one that promises to make those frustratingly wrong predictions a thing of the past. So let's dive into this revolution because it's being powered by the one technology that's changing everything: artificial intelligence.
And this chart, wow, it really puts a number on that feeling we all get. A one-day forecast? It's pretty much perfect, right? We're talking 97% accuracy, but just look what happens when you stretch it out. A week out, and we're down to 80%. And a 10-day forecast? Well, that's basically a coin toss, 50-50. Now, this isn't because meteorologists are bad at their jobs, not at all. It's because the weather is just fundamentally incredibly hard to predict.
So why? Why is it so ridiculously difficult? That's the big question, isn't it? And the answer, really, it comes down to one single word: chaos. The atmosphere is a chaotic system. Think of it as a giant, swirling pot of soup on a planetary scale. Tiny, almost unnoticeable changes in one spot can ripple outwards and create massive, unpredictable storms on the other side of the world a week later. Our traditional methods have been pushing the limits of what's possible, but they're starting to hit a wall. So here's how we're going to break this all down. First, we'll dig just a little deeper into this accuracy problem. Then, we'll look at how things have been done for decades, forecasting with physics. After that, we'll meet the new kids on the block, the AI revolution. And finally, we'll wrap up by looking at what this all means for a future with much, much better forecasts.
All right, let's start with the old guard, the established champion. This is the powerful, incredibly complex method that has been the absolute backbone of meteorology for more than 50 years. We're talking about simulating the physics of the entire planet's atmosphere. The official name for this method is numerical weather prediction, or NWP for short. And here's the best way to think about it. It's like creating a digital twin of Earth's weather systems. Scientists take all the current data they have, plug it into a massive simulation based on the laws of physics, fluid dynamics, thermodynamics, the whole shebang, and then they hit fast forward to see what happens next. But here is the massive problem, and it was summed up perfectly by the meteorologist Edward Lorenz way back in 1963. This is the heart of what you've probably heard of as the butterfly effect. It means that even the tiniest, most minuscule error in the starting data, like a temperature reading that's off by a fraction of a degree over the ocean, that error will grow and cascade and literally double about every 5 days until the forecast is just useless.
And this process, the scale of this operation is just monumental. First, you have to collect billions and billions of data points from everywhere: satellites, weather balloons, ships, radar. Then all of that gets fed into some of the most powerful supercomputers on the face of the Earth. These machines then spend hours, sometimes days, just crunching trillions of calculations to solve those physics equations and finally spit out a forecast.
So here's the key takeaway about the old way of doing things. While it's an incredible scientific achievement, it has two huge drawbacks. It is incredibly slow, and it is mind-bogglingly expensive. We're talking about supercomputers the size of a school bus running for hours just to produce one single forecast. And that really limits how detailed and how often we can get these updates. Okay, so if the old guard is this slow, powerful, but kind of clunky giant, what's the alternative? Well, let's meet the new contenders. These are the AI models that are completely flipping the script by taking a totally different and frankly radical approach.
And this is the real paradigm shift. AI models don't even try to solve all those complicated physics equations from scratch. Instead, they do what AI does best. They learn from data. They are trained on decades upon decades of historical weather data, a massive archive of what the atmosphere has actually done in the past. They analyze it all and just learn to recognize the patterns. It's like learning the rules of weather through pure observation, not calculation.
One of the very first big players to make waves in this new space is a model called Pangu Weather. It was developed by Huawei, and it was one of the first to show the world just how powerful this data-first approach could really be.
And we're not talking about a tiny little improvement here. As this quote says, Pangu Weather was a pivotal moment. It was one of the first AI systems that proved it could actually be more accurate than the best, most expensive traditional models out there, especially when you're looking a few days ahead. And that got everyone's attention.
Right on its heels came another absolute game-changer, this time from Google's DeepMind AI lab. It's a model called GraphCast, and it uses a slightly different AI architecture to achieve results that are just as revolutionary.
And this is where your jaw might just hit the floor. Remember those bus-sized supercomputers that take hours and hours to run? GraphCast can produce a more accurate
10-day global forecast in, wait for it, less than 60 seconds on a single machine. The jump in speed and efficiency isn't just an improvement, it's a whole different ballgame.
So let's just put them side by side. On the left, you've got the old guard. It's based on physics, it costs a fortune to run, and it takes hours. On the right, the new contenders. They learn from data, they're incredibly fast to run, we call that inference, and they're done in seconds. The difference is just staggering. It's changing everything. But there's a catch. Of course there is. This table shows a few of the top AI models. And while they are blazing fast to run, they are unbelievably expensive and time-consuming to build. Training a model like GraphCast requires its own mini supercomputer, running nonstop for weeks. This is not something you can just whip up on your laptop. It takes a huge upfront investment from some of the biggest tech companies in the world.
Okay, so this technology is amazing, it's revolutionary, but let's bring it back down to earth. What does a faster, more accurate global model actually mean for your daily life, for the forecast you see on your phone?
The benefits are frankly huge. It means you can actually trust that long-range forecast when you're planning a vacation or a wedding. Even more important, it means faster, more precise warnings for dangerous weather like hurricanes or tornadoes, which can give people more time to get to safety. This better data helps entire industries, from farmers planning harvests to airlines avoiding turbulence. At the end of the day, it just means more reliable information for all of us.
But this isn't a story about AI completely replacing the old way of doing things. In fact, the real future is probably a hybrid. As this quote puts it, the best path forward is a synergistic union. Think of it this way. AI can be the brilliant, super-fast scout that generates a dozen really good possible forecasts in seconds. Then, the traditional physics models can act as the seasoned expert, checking those forecasts to make sure they're physically possible. They make each other better.
And that leaves us with one final fascinating question. As these incredibly powerful tools become more common, what happens to the human forecaster? Will AI make meteorologists a thing of the past? Or, and this is what I think is more likely, will it free them up from all the heavy number crunching and allow them to evolve into a new kind of expert, someone who interprets these powerful models, communicates risk, and provides that crucial human judgment in an increasingly automated system? The forecast for that? Well, it's still being written.